Hello everyone, this is Dr. Webb. In this video we're going to be talking about one of the most important topics in the class, partial derivatives. And so this boils down to one of the basic reasons why we do calculus. So one of the big fundamental questions translated into functions of two variables is, given a function and a point, so given something in the domain, in this case the domain is a point on the xy plane, what happens to the values of the function as we move away from this point, as we move out of this point, move around this point. And so our strategy looking at it today in this video is going to be focusing in on what happens about changes in moving in the x direction and the y direction separately. So this is how we're going to change this. We're from Calc 1, we're very comfortable with one-dimensional problems. And so the way that we're going to take this two-dimensional problem, since we're on the xy plane, we can move in two directions around, is we're going to break them up and look at the x direction and the y direction separately. And that's going to turn this back into one-dimensional problems. Okay, so let's get a handle on this. So here's a function, x squared minus 3xy squared plus y cubed. And we're focusing in on the point 2, 1. And we want to know what happens to this as we change the x value, right? And so kind of think about doing this, taking derivative in terms of x. Okay, well, since we're only going to be changing the x, this y value, 1, this is going to stay the same. Right? And so we can plug in 1 for y, and we get x squared minus 3x times 1 plus 1 cubed is 1. Now this is a function only of x. And so this is what we're very comfortable dealing with in terms of Calc 1 skills. And so then we can take derivatives of it. So I can just do derivative of f, and I'm going to get 2x minus 3, right? And so this tells me the derivative of the function if I'm just thinking about moving in the x direction on this. And we could do something similar in terms of y. And so one of the things that this tells me is, if particular I care about what's happening at 2, I can go then and plug 2 into this. Evaluate this at x equals 2. And so that would be 4 minus 3 is 1. And so that tells me is, so remember, this is a slope, and this is talking about the change in the rate of the function at that point per change in x. And so this means at this point, as I change x, f is going to change at the same rate as x does. Right? The same rate being because the ratio between them is 1. And this essentially is what the partial derivative is. Right? So given a function f of xy, the partial derivative with respect to x is, and so because this is a function of two variables, we're not using the regular d's, we're using what are called partial d's. And so these are partial d's. Funky d, which pretty much is only used for partial derivatives. And so when we do this partial derivative, if you notice over on the right-hand side, we're changing the x values by delta x, but the y values are staying the same. These are y value is staying the same. And so what that means is that in practice, to take the partial derivative in terms of x, you take the derivative in terms of x, treating y the same way as you treat a constant. So treating y as a constant. Okay, and so some common notation, shorthand notation for this is this partial d of f over x. If we're talking about this taking place on a graph, and so we have z is equal to f of xy, then this is partial z over partial x. So this one is sort of analogous to the dy dx from Calc 1. Now, instead of doing sort of f primes to denote that we're doing this in terms of x, rather than putting a prime up, another common way, shorthand way, is to do a little x in the subscript in front of it. Or another way is using this capital D sub x. So this is kind of treating this as this is called a differential operator. So this is saying take the derivative in terms of x. And of course, we can do the exact same thing in terms of y. So we can define the partial derivative in terms of y is now we are treating the x's as constants. So kept, let's at least spell things accurately. So the x's here are kept constant, and the y values, you're changing the y value. And it looks exactly like the way you would take a definition of derivative in terms of y, and you have similar notation, except now you have y's instead of x's. Okay, so let's do this in practice. So this is the same function before. We're no longer focusing in on just one point, and we're going to calculate the partial derivatives f of x and f of y. So for f of x, f sub x, we're taking the partial in terms of x. So we're taking the derivative in terms of x, treating the y's as constant. So the derivative of x squared is 2x minus, so we're taking the derivative of 3xy squared. The 3y squareds are pulled out as constants. Derivative of x is just 1. And then derivative of y cubed, well, there's no x there, and so treat it as a constant. That goes to 0. Okay, so the partial derivative in terms of x here is 2x minus 3y squared. What about the partial derivative in terms of y? Well, x squared has no y in it, so if we're treating it like a constant, its derivative is 0 minus 3x gets pulled out because they're constants, but then derivative of y squared is going to multiply by a 2. I get a y there. And then the derivative of y cubed is going to give me 3y squared. And so this simplifies down to minus 6xy plus 3y squared. Okay. Okay, so geometrically, what are we doing in these partial derivatives? So let's draw out a quick plane, pick our point. Let's call that x naught, y naught. Let's say that we have some surface over that point. That's corresponding to something there. And so that's our point on the surface. Okay. So when we're doing the partial in terms of x, that means that we are treating y as a constant, right? And so really when we're treating y as a constant, really what we're doing is it's like we're slicing along the plane y equals y naught, is going to be a plane that's vertical and coming straight out. And this is going to slice through this surface as a single curve going through. And so now we have something one-dimensional, right? And so this curve right here is f of x comma y naught. The y naught is a constant. X is a variable. So we're down to one variable. So we can do the derivative same as we did there. And then what the value of the derivative is going to correspond to is the slope of the tangent of this line going along the plane. Right? So fx at x naught y naught is going to be the slope of the line at x naught y naught that's created when you slope of the tangent line created from the curve. Sliced by the plane y equals y naught. Okay. And then, so what's the partial derivative in terms of y? Well, then we're going to be fixing x naught. And so then take the plane x equals x naught. And so the plane x equals x naught in this case is going to be a flat plane parallel to your screen, cut through. And so this then is going to cut through and make some curve that's moving horizontally. And so this curve here is z equals x naught y. And so y is our variable. X naught is a constant. And so then the value of the partial derivative there in terms of y is talking about the slope of that horizontal tangent line. So you notice there's right now we have two separate tangent lines. We have a tangent line moving horizontal, which is the red one. And so that's moving parallel to the YZ plane. And so that's saying how much Z is changing in terms of Y. And then you have a tangent line that's kind of coming straight out towards us. That's the black one on the green plane. And that's telling us how much Z is changing with respect to X. Okay. And so we saw that when we took these partial derivatives, we get new functions with two variables, and so there's nothing stopping us from taking more and more partial derivatives. And so our second order partial derivatives, well, you could take the partial of x onto the partial of x again. So this is two partials in terms of x. And the notation here would be partial d squared f, partial dx squared. And so that's saying we took two partials in terms of x. And we might also write that as fxx. We could do the partial of y, partial in terms of y, of the partial in terms of y again. And we could have partial in terms, two partials of f in terms of y. We write that as fyy. But also we can mix these up. There's nothing stopping us from mixing these up. And so I can do the partial of y after I did the partial of x. And so we'd write this as I took the partial of y of the partial of x. And so in this, we took the partial of x first. And so I'd write it fx, fy. The reason why I'm switching these variables is over here, you're sort of reading, sort of like compositions. You read what's happening to f first. Well, I'm doing the partial in terms of x first, and then the partial in terms of y. Here, x is closer to f. So I took the partial in terms of x first, and then the partial in terms of y. And then we also can go the other way. Partial in terms of x, the partial in terms of y. And so we'd write it like this. And that would be fyx. And so there's different ways to go. And then we could keep going from here. And so these are our second order partials. For the third order partials, there's lots of them. So I'm just going to write them in terms of the f. Like that. So we have 3 in terms of x. We have xxy, xyx, fyxx. So I'm reading this one as I do y first, and then 2 in terms of x. Then we could do fx, y, f, y, x, y, f, y, y, x, and then the last one is do 3 in terms of y. Okay, and so this is all just talking about different orders in which we can do them. Fourth order, there's going to be, there's going to be 16 of them, so we could keep going up. So let's try this out. So let's just stay with the second order. So here's the same function we had before. And so before we saw that the partial in terms of x of this was 2x minus 3y squared. Partial in terms of y is minus 6xy plus 3y squared. So that's what we figured out before. And now we want to find the second order partials, right? So from the partial in terms of x, I can go in terms of x again. So I'm doing another partial in terms of x. That'll give me fxx. And I get partial derivative of 2x is going to give me 2 minus 3y squared. Well, I'm treating y as a constant, so that whole term is a constant, so it goes to 0. So the second partial in terms of x is just 2. And then I could do the partial in terms of y, and that's going to give me fx y. And so the partial of this in terms of y, well, then the 2x is a constant, so that goes to 0, and then I'm taking the derivative of minus 3y squared. I get minus 6y. Now over to fy. So I can do this 2 different ways. So one way is to do the partial in terms of y. And so that would give me 2 partials in terms of y. And so in this case, if I do the partial in terms of y, minus 6x is a constant times y, so I get minus 6x from that. Plus derivative of 3y squared is going to give me 6y. And then I can do finally the other mixed partial. And so that would be then taking the partial derivatives in terms of x. And so this would give me fyx. And so when I take the partial in terms of x, the first term, the minus 6y, is a constant. And then the derivative of x is 1. And then the plus 3y squared, that's all a constant, so that's derivative goes to 0. And so these are our 4 second order partials. And now if you look at this, the two mixed partials, fxy and fyx, they ended up exactly the same. They're both minus 6y, right? And so is that just lucky on this for this function, or does this always happen? And the answer is it's always going to happen that way. So, these conditions of f of xy is defined around AB, and the two mixed partials are both continuous around AB. These are very mild conditions. We'll see they pretty much always are going to hold true for us. And so then what that means is that then these mixed partials, it doesn't matter in which order you can do them. Okay, and so fxy is going to equal fyx. And so what this generally means is, so what really are our second order partials? Well, really we just have fxx, fxy, and fyy. What about for the third order partials? Well, since third order is just taking derivatives of the second order, and if f of xy is equal to f of yx, again, it's not really going to matter the order in which we took these partials, just the number of partials we took of each one. So we can take x 3 times. We can take x twice and y once. There should be no prime there. We can take x once and 2 y's, or we can take 3 y's. And so really for third order, there's only 4 partials. And then for fourth order, really deep down there's only going to be 5 partials. One doing all x's, 3 x's and 1 y, 2 x's, 2 y's, 1 x and 3 y's, and then 4 y's. Okay, and so this Clairaut's theorem that we saw in the last, or the Clairaut's theorem which we have right here, it really simplifies things down quite a bit. So when you need to take a mixed partial, it doesn't matter which order you do it, you're going to get the same thing both ways. And that is all I have for this video. I will see you again soon.